All right. So, let us recollect what were we doing in our last lecture. So, I defined a surface by a parametric equation r equal to r of u1 u2. Geometrically speaking, when you look at this equation, you will say that there is a function of two variable, means you have a function from a region of R2 and this is mapped to a space R3. So, this function will deform this rectangle into a shape like this. If this function is continuous 1 to 1, then that object in R3 is called a surface. Okay. We will assume that this function is in fact differentiable of class Cn. So, in order to do geometry, this is our requirement, that the function r belongs to class Cn. Moreover, we will also require that the product r1 cross r2, a vector, this should be non-zero, where r1 means the partial derivative of r with respect to u1 and r2 similarly means partial derivative of r with respect to u2, the second variable. We want this cross product to be non-zero. This is a topological constants. I will explain you why we require such a condition and what does it mean geometrically. All right, that we will be talking little later. So, this is the convention on symbols, and next I said that if a equation of this type f x y z equal to 0 will also represent a surface in R3, provided one of the partial derivatives of f is non-zero. So, if say if f z is non-zero, then implicit function theorem tells us that this equation can be converted into the form z equal to f x y. Now, these equations 1 and 2 represent the same surface. Okay. What I am given here is that the partial derivative of f with respect to z is non-zero. Similarly, if some other partial derivatives are non-zero, this will be either y equal to f of x z or x equal to f of y z, etc. So, these two functions capital F and small f are different, but both of them represent the same surface. All right, and this equation is called implicit equation of the surface, whereas this representation will be called an explicit equation. So, this is what we were discussing in our last lecture, and if you want to see these surfaces in parametric form, you can see it from here. I can write down a vector, position vector of an arbitrary point on this surface as x, y, f x y. So, here x becomes the first parameter u1 and y becomes the second parameter u2, and this is a small f of u1 u2. Then you can compute r1, r2, etc., etc. This will be 1 0 f x, this will be 0 1 f y. All right. So, these were the things which I told you in my last lecture. Now, the next thing that I will be talking about is the parametric curves over a surface. Parametric curves over a surface. So, as you have seen that a surface is obtained when you deform a rectangle into R3 or rectangular, or maybe it may be some other kind of region also. So, for simplicity, let us take a rectangle, and this rectangle means it is a product of Cartesian product of two intervals A B, Cartesian product C D, and this is being deformed through some vector valued function into R3, and the resulting object is a surface like this. Our equation of the surface is R equal to R u1 u2. The variable u1 varies on the interval a b, that is u1 lies between a and b, and the variable u2 lies between c and d. So, what I will be doing, so u1 is varying on this interval and u2 is varying on this interval c d. If I fix u2, suppose fix u2, that is I put u2 equal to some constant c, then inside the rectangle you will see this u2 equal to constant will be some line, and if I restrict my function over this line, it will be some curve. If you fix it somewhere else over here, for example, u2 equal to some other constant, its image will be somewhere over here. So, fixing u2 equal to constant, this will give you curves like this over this surface. Similarly, so this implies a curve. Why a curve? Because R will become a function of only one variable u1. Fixing u2, you will be getting a function of only one variable, a vector valued function of a one variable, and that must be a curve, and this curve is called a parametric curve. So, you have a family of parametric curves. Similarly, if you fix u1 as constant like this, suppose if you fix u1, you will be getting these lines, and the image of these lines under this function will be these curves. So, these curves over a surface are called parametric curves. So, put u2 equal to constant gives you a curve. Similarly, putting u1 equal to constant gives another family of curves. So, you get one family of curves over here by fixing u2 equal to constant, another family of curves by fixing u1 equal to constant. So, we have this entire surface is covered by a family of curves, two families of curves. So, this gives you a net, this gives a net of curves over the surface. This net of curves is called parametric curves. These curves are called parametric curves. And parametric curves consist of, so parametric curves consist of U1 curves. I will be calling a family of curves as U1 curve. This is the family when U2 is constant. Similarly, U2 curve, I will be calling U2 curves to those where U1 equal to constant. So, these two families together are known as parametric curves. Okay. Now, look at these R1 and R2 once again over here. If you want to see what R1 is, then now you can reply that R1 is nothing but the tangent vector to the U1 curve. Now, this can be noted down here that the vector R1 is in fact is a tangent vector to U1 curve. Similarly, and R2 is a tangent vector to U2 curve. So, we can see them what these vector R1 and R2 are, and these sometime are also known as basic tangent vectors on the surface. R1, R2, R1 and R2 are called basic tangent vectors. You will understand why we are calling them basic tangent vectors a little later. In fact, these tangent vector will become a basis of the tangent plane that we will be discussing little later. Okay. All right. Okay. Now, let us discuss the idea of tangent planes. There was one more point about this requirement. R1 cross R2 is non-zero. What does this requirement tell us? In fact, this cross product of R1 and R2 will be 0 only when either one of the vector is 0 or these two vectors become collinear. Now, R1, R2 are the tangent vectors. Suppose one parametric curve is like this and the other is like this. R1 is this tangent vector, R2 is this tangent vector. So, these are the two tangent vectors, and these two tangent vectors you can guess that they will always be linearly independent, because the two variables U1 and U2 are linearly independent, are independent variables, and therefore, the derivatives will give you distinct tangent vectors, okay, distinct in not collinear vectors. So, once they are non-collinear, this cross product will not be 0, and if one of them is 0, what will happen? That means, you have practically one tangent vector, other is becoming 0, and therefore, there is some sort of collapsing of the surface into one dimensional object. So, this will no more remain a two dimensional object, it will become a one dimensional object, and we do not want our surface to collapse inside R3, or some part of it we do not want, it is collapsing. So, that is why this requirement. Surface remain a two dimensional object, it may shrink, it may expand, but it should not be, it should not collapse to one dimensional object. Okay. So, this was the reason why we require this condition. Okay. They are also called coordinate curves. Okay. Yes, I am sorry. Okay. So, now we move on to, before discussing tangent planes, let us look at some examples of surfaces in parametric form and in implicit form, etc. So, some example. So, if you look at a sphere, for simplicity I will consider a sphere with center at the origin and radius as something a. So, this is my coordinate frame, x axis, y axis and z axis. So, the sphere is centered at the origin of the coordinate frame in R3. So, we know that we call it S2, and said theoretically it is the set of points in R3 such that x square plus y square plus z square equal to a square, or if you take a radius 1. So, this is the set of those points in R3 satisfying this. So, it is a football like shape, that is known as a 2 sphere or simply a sphere of dimension 2. All right. Now, so its equation x square plus y square plus z square minus 1 equal to 0, this is an equation of the type. So, the equation is of the type f x y z equal to 0. Here f x y z, the function of 3 variable is x square plus y square plus z square minus 1, which is 0. So, this you can say is the implicit equation of the surface which is a sphere. All right. You can convert into explicit form by writing z equal to plus minus under root 1 minus x square minus y square, where x y lying in a disk. So, x y x square, if I put the condition x square plus y square is less than 1, and they are positive also. So, okay. Huh? No, less or equal to 1. It will become z will become 0 when x square plus y square equal to 1. All right. So, that means x y lie in a disk of radius 1. So, a disk is being mapped to a hemisphere, upper hemisphere and lower hemisphere, and together it becomes a complete sphere. All right. Now, think of the parametric equation. For parametric equation, you need 2 independent variables. So, if I take independent variables as theta and phi, so suppose if you have a point P, there are some spherical coordinates in R3. So, what we do, if I join this point with the origin such that this position vector makes an angle say phi, okay, and this angle, and if I project it down into the xy plane, this is x axis, this is y axis, this is z axis, and suppose the projected part is this OQ. If OQ makes an angle theta, then I get 2 variables theta and phi. If I fix the length of the vector over here as 1, then these varying of theta and phi will determine a sphere. So, the position vector r, or you can say the x coordinate, you can determine x coordinate. What will be the x coordinate? In fact, you project it over here. This will be the x coordinate of the point P. If I take the length as a, for example, this length OP is a, then this OQ will be what? It will be OP cos 90 minus phi, pi by 2 minus phi. So, OQ will be equal to a cos 90 minus phi means sin phi, and this OX will be equal to, if I call it R, OR is equal to OQ cos theta. So, this become OQ is a sin phi cos theta. So, the x coordinate will become a cos theta sin phi, and this will be what? This will be 90 minus theta. So, this will be cos a OQ y equal to OQ cos 90 minus theta is sin theta. So, sin theta. OQ is a sin phi sin theta. So, y coordinate will be a sin theta sin phi. Okay. And similarly, you can see what is the z. Z coordinate will be equal to, z coordinate will be how much? This is the z coordinate. It will be a sin theta, a cos theta, so sin square phi. So, cos sin theta. Sin phi or sin theta? Phi. Sin phi. You can check it up that x square plus y square plus z square equal to a square. So, this becomes the parametric representation of the sphere. So, position vector of any point on the sphere of radius a is a cos theta sin phi, a sin theta sin phi, and a sin phi. I doubt cos phi, because this is 90 minus phi. Okay. So, this is 90 minus phi. So, this is a sin 90 minus phi. So, means cos phi, and you can check it up by squaring and adding. So, a square cos square theta sin square phi plus a square sin square theta sin square phi plus a square cos square phi. So, if you take sin square phi common from here, so this become a square cos square theta, a square sin square theta, only a square, and plus a square cos square phi. This becomes simply a square. So, we are right, it should be a cos phi. So, this is the parametric equation of a sphere of radius a. Similarly, I can write down the parametric equation of an ellipsoid. paraboloid, hyperboloid, all these conicoids.
Here we are finding parametric curves or
No, parametric equation of a sphere. A sphere is a surface. So, the question was what is the parametric equation. So, this is the parametric equation. The two parameters are theta and phi. Okay. Parametric curves also we can find out. If I put one of the variable as constant, it will give you a curve, that will be a parametric curve.
so you consider an example for explaining parametric curves.
No, I was discussing parametric equations.
Achha.
Okay. So, if you are interested in parametric curves, you can get that one. So, these are easy things. Okay. Next is ellipsoid. So, this is example 2, ellipsoid. So, ellipsoid all of us know is a surface, its parametric equation will be x equal to a sin u and cos v, y equal to b sin u and sin v, and z equal to c cos u. You can check whether it is correctly written or not, just consider x square upon a square plus y square upon b square plus z square upon c square. If it is 1, then the equation is correctly written. Here u and v are the two parameters of this. Now, other conicoids you can check by yourself. For example, I can leave it for you as an exercise. Find the parametric equation of number 1 of an ellipse of a paraboloid and a hyperboloid. A torus also, and you can also work out in general the equation of a surface of revolution. A cylinder and a cone, there are many conicoids, all of them are conicoids, all of them are surfaces. So, you can work out their equation. So, that you can try. Now, I come to the idea of a tangent plane to a surface. Okay. Tangent plane to a surface. As you have tangent lines to a curve, for this object surface we have a tangent plane. The defining idea is the same. Let us recall how did we define the tangent line to a curve. We said a line which has the highest order of contact with the curve will be a tangent line. So, we would look at the tangent plane in the same manner. If I fix up a point on a surface, we will look for the planes which has the highest order of contact with the surface. There will be many planes passing through a fixed point, but there will be only one plane which is important to us, which has the highest order of contact. Okay. So, in fact, the idea behind it is, suppose I have a surface here, if I fix up a point say P 0 over here, there will be many planes which will be passing through it. I suppose this plane is passing through it, this plane is passing through the point P 0, and there will be various other planes. But we have to see which plane is the nearest to the surface. Nearest, I am using a term nearest. This term is to be explained mathematically. In fact, what I will do, I will take a variable point in the surface and will look at the distance of this point with the plane. If I compute the distance of this point from this plane, it will be larger distance, and moreover, when I take this limiting case when p approaches to p 0, I would like that this distance should go towards 0 faster than the distance p 0 p. This will happen when this tangent plane sits close to the surface. This is basically the idea. Okay. We will put it more formally. So, let r equal to r of u1 u2 be a regular surface, okay, and be a surface. It may have singular point somewhere, we do not mind, but the point where we are looking for a tangent plane must be a regular point. Okay. Let this be a surface, and P 0, whose position vector is r of something u1 0, u2 0, this point be a regular point. Of the surface. So, now I define the official definition of the tangent plane first, then we will elaborate. A plane passing through P 0 is said to be a tangent plane, to the surface. Let me denote the surface by a symbol sigma. Usually we denote a curve by C and a surface by sigma. So, P 0, this plane passing through P 0 is said to be a tangent plane to the surface at P 0 if it has, we do not call it a contact, in fact, we whose distance from P. So, I have to take another point. Let me write down over here itself, I have fixed up a point P 0, and thirdly, P be a variable point, be some variable point, a variable point. If the distance the distance of P from this plane is of highest order of smallness, highest order of smallness. A plane passing through P0 is said to be a tangent plane to the surface at P0 if the distance of P from this plane is of highest order of smallness. So, the defining condition is the underlined statement. This should be understood, okay, what it means. So, all right. So, let me do it here. So, let us try to understand this underlined statement. So, what I have done, let me draw the figure again. Suppose I draw this plane which passes through the point P0. I have chosen another point P on the surface, and the position vector, suppose origin over here, this position vector is r of u10, u20, and the position vector of the point P is r of u10 plus something h, u20 plus something k. Okay. These are the position vector. Now, look at this difference. This is the distance between P0 P. So, the distance P0 P is a vector OP minus OP0. So, this is in fact the distance. Okay. So, this is r of u10 plus h, u20 plus k, and minus r of u10, u20. Okay. Now, if you are interested in the straight line distance between P0 and P, it will be the length of this vector P0 P, and this must be h square plus k square under root. The length of the vector P0 P will be under root h square plus k square, straight line distance. Okay. All right. Then what you do, you drop a perpendicular from P onto the plane. Let me call this plane as pi. Okay. So, let pi before writing pi, the equation of a tangent plane and equation of a plane passing through P0 is given by the equation of a plane through P0 is given by, if you want to write down the equation of a plane which passes through some fixed point P0, okay. P0 ko I will write down r of u1 u2, or I can mention it as r naught, no problem, dot n. equal to 0, where n is a normal to the plane, where you call it number 1, where n is a normal no.
So that is in this equation when we write r minus r naught dot
The
product with the perpendicular line.
that is an equation of a general plane.
General planes.
Yes, if you want to write equation of any plane,
Yes.
you will see which point it passes and to which vector it is orthogonal. If these things are known to us, we can immediately write down the equation of the plane. Okay. So, this is some plane which is passing through R 0 and perpendicular to n. So, its equation must be like this, where n is normal to the plane. Okay. Now, the perpendicular distance of P from this plane is what? The perpendicular distance of P from the plane is what? In fact, I have considered a vector capital N which is orthogonal to the plane. Now, I am interested in this distance d. Okay, d is the distance of the point P from the plane. This is perpendicular distance. So, if I see the direction of this vector, since I have dropped a perpendicular, it must be parallel to n and its length will be the distance between P and the plane. Okay. So, what I will be doing in order to measure this distance, I will project the vector P 0 P onto n. So, what you do? You draw your normal n from here, and then you want to find out this distance, drop a perpendicular. So, this distance, the projection of this vector P 0 P, this projected point will be somewhere over here. So, this will give you the distance d. So, the distance d from the point P to the plane is d equal to the projection of P 0 P onto n, and this can be written as what? P 0 P is how much? It is r of u10 plus h u20 plus k minus r of u10 u20. This is the vector P 0 P dot n divided by modulus of n. This is d. Okay, this was number 1 and this is number 2. Okay. So, I stop here for the first part of my lecture. We will continue in the second part. We stop.